The groups of the periodic table are each vertical column, and we also call them families. The elements in a group have very similar physical and chemical properties. For example, the elements in group 1 or 1A, depending on where the nomenclature comes from, which are hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. All of those elements have the same number of electrons in their outer shell. We'll cover those later on, but because of that, they have very similar chemical reactivities. Lithium, sodium, potassium, rubidium, cesium, and francium all react with water extremely vigorously and even potentially explosively. They are all solid metals. You can cut them with a knife, like a butter knife, or even your finger could probably push through potassium, rubidium, cesium, and francium like it's a soft butter. And densities and melting points and things like that are similar in a sense, so that's why we group these things together. The group numbers are written above each group at the top of the periodic table, and as it says here, there are multiple different conventions for their labeling. Your book has groups 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18, but it also has 1A, 2A, and then it goes to 3B and through 8B, and then back to 1B and 2B, and then 3A to 8A. That's the oldest method, and there is some practicality to it for why it goes 3B, 4B to 8B with three groups of 8B, and then back to 1B and 2B, and then up to 3A and 4A, and so on. There's reasons for that that describe the chemical nature of these elements, but people didn't like it because it's confusing, so they renamed it recently to just 1 through 18, and that's probably what I'll use for the rest of this class. The representative elements are groups 1, 2, and 13 through 18. They're called the representative elements because most of the elements that we use or interact with or encounter in our daily lives are in those 8 groups. Now, obviously, we do need things in the transition metal stage of the periodic table, but they're not very common in our bodies or for what we need to survive, so that's why they're not representative elements. But the transition elements are the central block of it, groups 3 through 12. The lanthanides and actinides are below the periodic table. We won't really discuss those because they're not super important. Periods are each horizontal row of the periodic table. The elements within a given period have varying properties, meaning they're constantly changing from one element to the next. But those properties are repeated in each row, whether it's above it or below it. Like I said, lithium and sodium and potassium and rubidium, those react with water very vigorously. Beryllium and magnesium and calcium also react with water, but less vigorously. But their reactivities with it are going to be similar to each other. But either way, as you go across, boron, carbon, nitrogen, oxygen, fluorine, neon in that second row, they don't react with water. So you could go from lithium, which is fairly reactive, all the way down to neon, completely unreactive, and then you get back to sodium where it is reactive again. And then magnesium is barely reactive with water, all the way to aluminum through argon are not reactive at all. Back down to the next row, you have potassium, which is reactive again with water and explosively. This is why we call it the periodic table. These properties repeat periodically. There are 7 rows of the periodic table. The 2 rows that are below, the lanthanides and actinides, would actually be between groups 3 and 4 in the transitions elements part of it, but it would make it hard to fit all of the elements onto a page and actually be able to see everything, so they took them out and put them below. And they have different electronic properties and things like that than the rest of the transition metals, so they don't belong in there anyways. They belong separately with themselves. All right, some names of the groups. I already mentioned them earlier, but group 1 is called the alkaline metals. Group 2 is the alkaline earth metals. It's a stupid distinguishing name from the first one, I think, but alkaline earth metals are called earth metals because you could say that they come from the earth. They're not reactive with water, and things that are not reactive with water, back to the ancient Greeks, were called earth, or their elemental form was of earth, and we'll get to that topic later. Whereas the alkali metals, they are very reactive with water, and so they would actually be obtained from sources of water, so they're not alkaline earth metals. Group 17 is the halogens, which has fluorine, chlorine, bromine, iodine, and astatine. And then group 18 is the noble gases. Those ones are not reactive, they're inert, hence they are noble. So that's group 18. This here periodic table just shows you those groups. It actually says that there are no common names for groups 13 through 16, but that's not true. There are common names. They're just really weird and hard to pronounce, so I'm not going to give you those to worry about. All right, also in the periodic table, we can separate the elements by metals, nonmetals, and metalloids, or semi-metals. Metals are elements that are shiny when they're solids. Even a liquid, they can be shiny, but they're shiny, lustrous. Let me put those words together. There we go. They're lustrous. Metals are ductile, meaning that you can squeeze them through tubes, and this is how they make wires. They actually take a metal and they put a lot of pressure on it and squeeze it through a tube, and it forms that wire shape. They're malleable in the sense that you can take the metal and hammer it from one shape to another. You can take gold, for example, and you can hammer it down into like aluminum foil type material, so gold foil. And it's very easily done with gold, which is why you see Olympic athletes, when they win the gold medal, they always bite it, because if you had pure gold, you could easily bite into it and compress the metal structure. Whereas silver and bronze, those you can't. At least not as easily. Metals are conductive to heat and electricity. I'm sure you can easily know what this means. That, like, if you put a metal pan on your oven stove and you heat it up, it doesn't take long for it to get hot. Whereas if you were to take a piece of wood and heat it up, it takes a long time to heat that up. This is why your clothings are insulators, because they're made up of these non-metallic materials, so they don't conduct electricity and therefore they don't conduct heat. They keep you warm because the heat can't pass out of your body to the atmosphere as easily. Whereas if you were wearing metal as your form of clothing, you would conduct your heat out of you very quickly, and you would get colder much faster. Metals have high melting points. They usually have high densities, and the only one that is a liquid at room temperature is mercury. There are none that are gases at room temperature. The nonmetals basically have the exact opposite properties of metals. They're not lustrous. They're dull if they're a solid. Although that's not always true, but it's sometimes true. Carbon is a nonmetal, but if you look at pencil lead, if you look closely at it, it is kind of shiny. Iodine is a metal that is definitely shiny and looks like a metal, but it is not. Carbon in the form of diamond does not look like a metal at all, but I wouldn't say it's dull either. I would say it's brilliant. Phosphorus and sulfur, though, they are dull as solids. They're not ductile, they're not malleable, they don't conduct electricity or heat, so hence these nonmetals are insulators. They have low melting points, and they have low densities. Most of the elements that are nonmetals are gases at room temperature. The only solids at room temperature are carbon, phosphorus, sulfur, selenium, and astatine. And the only one that is a liquid at room temperature is bromine. The metals and semimetals have properties of both metals and nonmetals, or they can have properties that are in between metals and nonmetals. So they can conduct electricity, but they're not as good as metals. They're semiconductors. So they can conduct electricity fairly well, but not great, or they can actually not conduct electricity at all. And so an example of that would be silicon. Silicon is a semi-metal or a metalloid. It can conduct electricity very well in some forms, but in other forms it doesn't at all. It's used in your computer chips to conduct electricity there. Carbon is not a semi-metal, but in my opinion it should be, because you have graphite, which looks somewhat metallic. It does conduct electricity extremely well, and in fact the best known conductor of all the elements and materials that we know of is an allotrope of carbon called graphene, which is a 1 atom thick sheet of carbon that is bonded similarly to graphite, and it is the best conductor of electricity. On the other hand, the diamond form of carbon, the diamond allotrope, that one doesn't conduct electricity at all. So the form of carbon there determines whether it is going to be a conductor or an insulator. It should be a semi-metal, but it's generally not considered to be one. As this picture shows, the only elements in the periodic table that are metalloids are boron, silicon, germanium, arsenic, antimony, tellurium, polonium, astatine, and tennessine. Although tennessine is not something that we really know anything about. There's only been a handful of atoms of it ever even made and witnessed. So I wouldn't myself call it a metalloid until we know more about it. Alright, and so this table here shows you some comparative properties of a metal, a nonmetal, and a metalloid. Silver is the metal. It's shiny, it's extremely ductile, it can be hammered into sheets, so it's malleable, it's a good conductor of heat and electricity. It's very good, actually. It's used in coins, jewelry, tableware. It's got a high density and a high melting point. Antimony, the metalloid, is shiny, it's brittle, it's not strong and hard like the silver metal. It is not malleable, it shatters when hammered. It's a poor conductor of heat and electricity. It's used to harden lead, color glass, and plastics. It has a intermediate density, and it has a fairly high melting point. I would say that's very high, but not nearly as high as silver is. Sulfur is a nonmetal. It's, as a solid, dull and yellow. It's brittle. It shatters when hammered. It's neither a conductor of heat nor electricity, so it is a good insulator. It is used in gunpowder, rubber, fungicides, and it's responsible for many very stinky things like The smell of skunk has sulfur atoms in it. It has a very low density and a much lower melting point than the others. The key terms that I've covered in this lecture are the alkali metals, the alkaline earth metals, chemical symbol, group, group number, halogens, metals, metalloids or semimetals, noble gases, nonmetals, periods, periodic table, representative elements, and the transition elements. These are some of the problems that are in the book that I feel like you should work on, outside of the ones that are within the context of the chapter itself. I haven't separated them into which ones have been in this particular lecture or not, but please work on these when you get the chance.